Okay, guys. So today we will study delay differential equations. Uh, the key point is, ordinary differential equation will help you, in order to, let's say, have evolution of your dynamical system at, at current time and, of course, at the current state, actually. But unfortunately, ordinary differential equation will not capture the things which are are going to happen in the past. So for instance, you cannot let's say check the behavior of your dynamical system, or let's say the evolution of your dynamical system uh, for the past values. So in such case, we need to study delay differential equations. Okay, so I will give you, a brief introduction of delay differential equation in the very first part, and then we will see analytical treatment of delay differential equation. We will see a few analytical methods like the method of steps, search for, let's say, the exponential solutions and the Laplace transforms. Okay, and in this lecture, we will not see, let's say, the numerical treatment of delay differential equations. In the second part, we will consider a very simple case when we have, let's say, a linear delay differential equation and dimensionless form. So you can even, imagine how simple case we will study. And then, we will try to study the stability analysis of delay differential equations, okay? We will see MATLAB solvers in order to study delay differential equations. But of course, I mean, as I mentioned earlier, that we will not see, a numerical treatment in a great detail. So after that, I will share with you a few, I guess they are the important links if you want to study, more on delay differential equations. And finally, a couple of exercises if you like to solve. Okay, so let's begin with our first part, and we recall, ordinary differential equations. And we know that, ordinary differential equation will help us, let's say, to study the evolution of, let's say, our dynamical system at the current time and at the current state. Okay. For instance, you can see here that this the time derivative depends only, I mean, these two guys. Okay, the current time and the current state of your system. So this means that unfortunately, we have no dependency on the past. Okay. So similarly, for instance, if you want to let's say something about maybe incubation, life history, or duration of events, then I mean ordinary differential equations will not give you let's say much information. Okay. Or you can say that anything that going to happen in the past, but of course, let's say it is very important for the current evolution of your system under consideration. Then, of course, you have to give a look at let's say delay differential equations rather than ordinary differential equations. Okay. Even, I mean, let's say, in nature, the things, they don't happen actually, instantaneously. So for instance, you can think about, let's say, biology. So in biology, the changes doesn't occur instantaneously. just think about, the birth of the human. I mean. So, well, that, the birth rate of, let's say, of the humans, it depends on, the resources which are available at the time point. Okay, so unfortunately, these kind of, you can say that situations, they are not captured, in a good manner with the help of ordinary differential equation. Okay? So for that, we need, delay differential equation. It is basically, you can say that an ODE, although at a later stage, we will see, the key differences between delay differential equations and ordinary differential equations. But allow me to say that at this stage, let's say, delay differential equation is basically, ordinary differential equation where, your time derivatives not only depend on, the current time and the current state, but of course, I mean, it also depends on the state and the past. So here, this, let's say, parameter, tau, it's lag, or you can say that it's a delay to your system, okay? Okay, so if delay is constant, let's say some number, then of course your delay differential equation is of this particular nature, a constant delay differential equation. Okay, but on the other hand, if your delay depends on your this independent variable, then you will have a time dependent delay differential equation. Okay. Similarly, for instance, if your delay over here, it depends on let's say the current state of your of your system, then you have to study the differential equations which are basically the state dependent. Okay, so here we consider a discrete version of delay differential equation, but it's more complicated compared to, let's say, this case, because in this case I can imagine only one delay, but here I can have, let's say, a bunch of delays, like I mean, let's say tau 1 and then so on and so forth. Okay, so of course it's more complicated to study this kind of delay differential equations, because you have to move in the past. Okay, also your delay differential equation, so we can also have these guys. So these are the derivatives at those delays actually. So for instance, I can take this j from n plus 1 to n. So I can have too many delays, and this special case when we have the involvement of the derivatives, then our delay differential equations are of neutral type. Okay, so although I mean we will not see in a great detail these a neutral delay differential equation in this lecture. This is basically the continuous version of your delay differential equation, and in this case we have to consider this function phi, which is basically the history function, and this history function will give you information about what's happening in the past actually. So for instance, if you have a current time, then of course I mean you need this history function to say something about the past as well. Okay, for instance, when you just simulate simple, let's say, ordinary differential equation, then of course you need to set up initial value problem in order to compute unique solution at some particular let's say interval. Okay, So for instance, let's say for this time, okay, so you can set up, initial value problem. And the point is, over here, the initial values are basically, given at some initial point actually, okay? But on the other hand, if you have, let's say, a delay differential equation, then, you can set up an initial value problem. But the point is, for, let's say, initial values, you need to, let's say, construct this, initial function, which is basically the history function for, the negative times actually. So for instance, if I take this time to be positive over here, then of course I have to take this guy to be negative, okay? So somewhere in the past. Yeah, this is your history function. Okay, so for instance, if you want to, study this delay differential equation, then, your initial datum, or let's say your, history function. So you have to define it on some particular interval line. So for instance, if you take this time, let's say t naught, then you have to, consider the previous times as well. Okay, and in this case, you will see that your history function is basically, it has, a deep connection with, you can say that, the current state of your system, actually. Okay. There is another point, and the point is that, we can have, jump derivative discontinuities at, let's say, this particular time, even if we consider that our function and this guy, which is, the initial history function, even they are smooth. Okay. For instance, okay, yeah. So it will be clear from this particular example, actually. Okay. So over here, I mean, this guy and this guy, they are the lags or delay to our delay differential equations. And for instance, if I choose, this guy as to my initial function or history function, okay, for negative times, then I can set, the things like, let's say I can have, let's say my initial function to be 0 for negative values, and at the origin, let's say it is, exactly equals to 1. Okay, then you will see that we will get actually, these jump discontinuities at these points actually. Okay, so for instance, if you see here, so for the negative times, my history function is 0, but at a time t is equals to 0, let's say my history function is 1. And then you will see that at these points, 0.2 and 0.33, which are basically, these two legs, you will see that I have actually, these jump discontinuities. Okay. And then in this particular case, let's say I have this, kind of smooth kind of, the behavior. Okay. The dynamical structures of delay differential equations, they are actually much richer than, the dynamical structures of ordinary differential equation. So for instance, if you consider, ordinary differential equation, okay, the bounded solutions of your autonomous, let's say, systems, so they can oscillate, when you have at least, the two components. And for instance, you need at least three components in order to have this, the chaotic solutions. Okay? But if instead of ordinary differential equations, we have the delay differential equations, then even in a very simple case, let's say a scalar case, we will have both kind of behaviors. Let's say the oscillatory behaviors and the chaotic behaviors of our system. Okay, so let me give you some important differences between ordinary differential equation models and delay differential equation models. Okay, so for instance, in case of ordinary differential equation models, so if we assume that the effect to any change to our, let's say, dynamical system is basically instantaneous, but unfortunately this is not true when we have the delay differential equation model. So for instance, you can just think about the history function, because you have to take into account past. Okay, also in ordinary differential equation models, so basically they will generate a finite kind of system actually. So you will have basically a finite dimensional systems, but over here you will have let's say unfinite dimensional systems. Okay, and your ordinary differential equation models, if you want to determine, let's say, the unique solution, then of course you have to set initial value problem, but the point is the information is given at some particular point actually, the time point. But on the other hand, if you want to have a unique solution, so you have to basically construct the history function rather than, let's say, a point actually. Okay, you can take a simple case when your history function is, let's say, a constant, some number even. Okay, so let me give you some important applications of the various types of delay differential equations. Although we will not see in a great details these the special types of delay differential equations, but of course, I mean, one can give a look. You can search it. Okay, so the delay differential equations of this type, I mean the retarded delay differential equations, so they have important applications in radiation damping and the modeling of the tumor growth. Similarly, for instance, the modeling of HIV infection and biomodeling. So one can use these kind of delay differential equations. Okay, so similarly, for instance, and PLR, or you can say that the immune responses, blood cell production. So one can use the stochastic delay differential equations. Okay. Let me also give you some important applications of delay differential equations for the different types of delays. So we can have even the different or the various types of delays. So for instance, if I take this single fixed delays, then I can use such kind of delay differential equations in order to study let's say immunology. Okay, similarly, for instance, I can study cancer chemotherapy, and then I mean infectious disease modeling, and let's say the lifespans of the population models while using multiple fixed delays. Okay. Similarly, for instance, the combustion and the chamber of turbojet engine. So you can use basically these delay differential equations, which going to have delays which are basically varying delays. So you can say that they're basically the state dependence. Okay, so over here you have basically the time dependence. Okay, so now we will see the analytical treatment of delay differential equations. And we know the fact that, in real life problems, we have, of course, delays, and they are, of course, very complex in nature. Okay. However, we will consider a simple case. Okay. So we will take, the delay differential equations which have constant coefficients. Okay. And in order to study, this kind of delay differential equations, so, several approaches are available. We will consider three of them. So we will see a method of steps. So this was initially developed by Bellman and Koch for especially, these kind of delays, the variable delays. Okay. And similarly, one can also, search for the exponential solutions for your, delay differential equation in order to have, the analytical solutions. Similarly, one can also use, the Laplace transform methods in order to have, the analytical solutions of your delay differential equations. Okay, so we will begin with the method of steps. So first we will see its, a summary, and then we will attack at least maybe 2 examples with the help of method of steps. Okay, okay. So we consider, this special case of delay differential equation with constant coefficients. Okay, which are defined over this time. So I take P is positive. Okay, and my initial function or the history function is defined over this interval. So these are, the past values. Okay, since we are, interested to give a look for a continuous extension into the future. Okay, so first we consider, this particular interval. This is T naught plus tau actually. Okay, so on this interval, you will see that our delay differential equation will basically, reduces to an ordinary differential equation. Okay, and then we will try to find the solution, the valid solutions, on this particular interval, and then we will make use of this solution as, of course, as an initial function for this particular interval, because this is, this guy, and then at the next step, of course, we have to move over here, and then we will, continue this process. And once we are able to, find the solution over this interval, so in this way, the solution is extended forward from interval to interval. So it is basically, a step-by-step method. Okay, so we will continue this process until, we will get a solution of ordinary differential equation which is valid over this interval. Okay, of course we have, expanded the things. Okay, so but the key point is, we have to solve, an ordinary differential equation at each and every step. So we cannot skip this actually. For instance, if you want to search for, let's say, a unique solution, okay, and it will guarantee a unique solution. Okay, so for a better understanding, let's take this example. So here we have this, a simple delay differential equations, and from the equation, it's clear that our delay is constant. It's 1. Okay, and let's say I give you the history function, which is this guy, and for all t belongs to this interval. It's true actually for all t. Okay, and then I choose an interval, let's say this guy, and I can reduce my, delay differential equation to an ordinary differential equation. So over here, I mean, you will see that this guy will take basically this particular format. So this guy is basically, let's say it's 1, because at initial stage, your history function is actually 1. Okay. Of course, here t is basically, and this particular interval. So this is your initial history function. Okay. And now, in order to search for, this current state, of course, we have to use this, the integral form of the solutions. Okay. So if you use the integral form of the solutions, okay, and while I mean, of course, you have to use this guy as a history function, then I mean, you will get, this integration as t actually. So you will get from this value as a t, and you can compute this guy, because from this guy, I mean, this is valid for all t from this interval. And if I take this guy, then of course I will get, let's say, x of 0 is equals to 1. Okay, so I will get an expression for this guy, which is basically, let's say, linear 1 plus. Okay, and now I will continue this process. Okay, and I write my delay differential equation on the next interval, which is 1 to 2, because initially I have 0 to 1. And now I have the next interval, which is 1 to 2, okay? Then, my delay differential equation will reduces to an ordinary differential equation. And now over here, you will see that this guy basically is defined over this interval, okay? And x of t is basically 1 plus t from the previous step. So therefore, my delay differential equation can be written as in this particular fashion. Okay, so now my next history function, which is phi1, is 1 plus t, and t is from 0 to 1. Okay, and if I use the integral form of the solution, then you can say that the behavior of the current state is basically, this guy. It's non-linear. Okay. So here, phi1 is basically, this guy, 1 plus t. And if you do its integration, so over here, you will get, s plus s squared by 2. Okay. And then you use this, the limit of integration, you will get this expression. Of course, this factor will appear from, from this condition, because you know that at time t, so x of t is equal to 1 plus t. Okay, so if I take time t is equals to 1, then I will get this guy to be 2. Okay, so similarly, if I continue this process, and now I take the interval which is 2 to 3, and then I can also derive an expression for the current state for this interval. So this is a mistake. Okay, so if I do that, then I will get the following, of course, the nonlinear expression for this guy. Okay, because my the second you can say that the history function is this guy. Okay, but now the point is, I mean, you can continue with this process, and maybe you can eventually arrive at the general form of your desired solution. Okay, so now rather than let's say constant history function, I can have basically history function which is of let's say this particular class. Okay, and this particular interval. So I have a history function which is this guy over. Okay, so Now the point is, I mean, if I want to, search for the solutions to the given delay differential equation with these above initial function or the history function, so you will see that my history function will be of the class this one, of course, over this open interval. So this is up to n plus 1. So I will have n plus 1, where n is basically, a natural number. Okay, so in order to compute a solution on this, let's say, a closed interval, so 0 to 1, we take, initial datum on this interval, which is, let's say, this guy, your history function of class, let's say, this guy. Okay, then, your solution on this open interval will be of class, basically, p plus 1. Okay, so if you just continue this process, so for instance, you move at the next interval, which is from 1 to 2, then your solution is of class, you can give a look over here, it's of the class p plus 2. Okay? And then, you can carry on this process. So as a next example, we take this, a spatial delay differential equation, and I have here a positive time, and my history function is this guy. So it's let's say linear. Okay, and now you have to use method of steps in order to find the solution for this guy and this let's say particular interval. Okay. So we will not see the point-wise detail, but over each and every interval, we can have basically a history function, and then we will obtain an ordinary differential equation while reducing a delay differential equation into an ordinary differential equation, and then eventually we will have its solution. Okay, so for instance, if I take this interval. Okay, since my history function for this interval is a constant, okay, then for this particular interval, my ordinary differential equation is in this particular fashion. Okay, then my solution will appear in this particular fashion, and you can move from interval to interval, and you will get your required result. So, for instance, for this interval, you will see that your solution is basically this guy for delay differential equation. Okay, so let me give you an exercise, and I just slightly vary this history function. Let's say it's this guy, and the interval is this 1 to 5. So please try it. Okay. Okay, so our second method is basically, this Laplace transform methods. It's the analytical treatment of our delay differential equation. I consider a very simple example, which is basically a first order delay differential equation. If we take the Laplace transform of this delay differential equation, then this will lead us to an equation of this particular fashion. Okay, and now I make use of the change of variables on the right hand side of this equation. Then I will get an equation of this fashion. Okay, so furthermore, I can maybe pay attention on this guy, and I can assume the fact that for large t, this guy basically has this the asymptotic behavior. Okay? So then eventually I will get this kind of expression for my equation under consideration. Okay, and furthermore, I assume that this factor is non-zero. Then I will get eventually this kind of expression for this guy. because my goal is, to write down an expression for this guy, the current state of your, dynamical system. Okay, and in order to get an expression for this guy, I have to, make use of the inversion formula. Okay, so eventually I will get, the expression for the current state of my dynamical system. Okay, so now you can say that, the solution of your delay differential equation can be expressed in the terms of, the initial values of your state over this interval with the help of, a contour integral. Okay. Okay. So next we study, the stability analysis of delay differential equation while consider this, the simple case of linear delay differential equation in dimensionless form. Of course, one can target, other kind of linear delay differential equations. Okay. Okay. Now the key point is compared to ordinary differential equations, the stability analysis of delay differential equation is more challenging, and the reason is straightforward. That's basically, unfinite dimensionality of your system, because as you know, at the initial stage of the lecture, I mentioned that, the delay differential equation models, so they give you basically, unfinite dimensional, system. So here we take a very simple, example. So this is a linear, of course, and dimensionless form. So consider this example. So here, this guy is basically, in this particular fashion. So of course, we have the lag, which is 1. Okay. So if you just, analyze this differential equation, so immediately, you will get the fact that the only equilibrium point for this, delay differential equation is basically this point. But now the question is basically, I mean, either this equilibrium, let's say, solution is stable or unstable. Okay, we don't know that. So, for instance, you can just assume, I mean, let's say you are at the top of this, the hill, and if this guy is your equilibrium point, but a small perturbation to this equilibrium point can lead us to, let's say, of course, to unstable situation. But on the other hand, I mean, it's possible that, let's say, just consider this, the situation of, let's say, maybe the convexity actually. But if you have at this point, I mean, then a small perturbation, I mean, of course, I mean, the small perturbation will not disturb, your, let's say, system, and still you have, stability. You can just think about maybe, this the simple harmonic motion. Okay, so I mean, if you, let's say, start near, then you will basically, stay near actually. Okay.
Okay, so now we try this exponential function as, one of the candidate as a solution to our delay differential equation, and then in view of the time derivative of this guy, we will get the characteristic equation as follows. The solution to this characteristic equation will give us basically the eigenvalues to our system of linear ordinary differential equation. Okay. Now for ordinary differential equation, this characteristic equation is basically a polynomial, And then in order to find, the number of eigenvalues, one can use this, the fundamental theorem of algebra. For linear DDE differential equation with this, the characteristic equation, which is basically, a transcendental equation. So maybe one can use, this the lambda W function in order to compute, its solution, which are basically, let's say eigenvalues in our case. So now we can consider, both real and complex solutions separately, and then we will study, the stability analysis. So first I consider that, our eigenvalue lambda is real. Okay. So if eigenvalue is real, then I need to search, for a point of intersection for this line and this curve. Okay. So for instance, if I choose this parameter to be positive, okay, and then I will have a single intersection at the positive value of the eigenvalue lambda. And then, my exponential solution, it will increases for large t, and our equilibrium solution is basically unstable. Okay, I have here, the eigenvalue, which is basically, you can see it's negative over here. Okay, while on the other hand, if this parameter is negative, then I will get basically either no point of intersection for the curves, and I will have either one or two, intersections. So, for instance, you see here, if lambda is real and A is positive, then between Z is equal to lambda and this, exponential guy, we will get, a point of intersection over here. And if, I have lambda to be real, okay, on the other hand, if A is negative, so for the three values of A, which are negative, so for this curve, I have no, a point of intersection. It's very clear. And for this black curve, I have 2 points of, intersections, but this guy is special. So for this guy, I have, a point of intersection with this line, which is Z is equal to lambda. And this is basically, tangent to this curve. Okay, so at A is equals to AC, this, this on the red curve. Okay, so we have a point of tangency. Okay, and if A is, less than this guy, then we have, no real roots. For instance, you can see something for this guy. Okay. Okay, so when curves are tangent, so we have, a single intersection, so which is basically, at the point of, tangency, the curves have, same slope. So for instance, for the line, we have 1, okay, and from this, at the point of tangency, we will get, the following expression for this parameter A, in terms of course, the eigenvalue lambda, which is real in this particular case. So this means that, on curve Z is equals to A times e to the minus lambda. If I just replace, this parameter A, of course, with this fellow, then you will see that Z is equals to -1. Okay. And since we know that, this intersection is, exactly on the line Z is equal, on the line Z is equal to lambda, and lambda is equals to, -1, because Z is equal to -1. So this means that my eigenvalue is real, but it's negative. Okay. So therefore, I can say that, tangency occurs at this point. Okay, so this is, you know, your negative eigenvalue, -1. Now, if I choose A and this particular, you know, manner, then you will get two negative eigenvalues. Of course, they are real in nature. Okay, and if I choose A, which is exactly equal to, let's say, A sub C, which is the point of tangency, so then I have one eigenvalue which is negative. Okay? And if I choose A, which is less than the point of tangency, then you will see that we will have no real eigenvalues. So, for instance, it's very much clear from this picture. Okay. So now I can make use of superposition, and then you will see that, you know, the solution for a delay differential equation can be expressed as the sum of these, you know, exponential solutions. So if I take A from this, you know, interval, then you will see that the eigenvalues are negative. Okay, so this means that, you know, we will have basically exponential solutions decay to 0 over the time t actually. Okay. Now the point is, I mean, if I take A of this particular nature, then, you know, we don't have, let's say, either exponential decay or exponential growth for the components of our solution. Okay. So now, on the other hand, if I assume that, you know, the eigenvalue is complex, okay, then I can go back to my characteristic equation, and then, you know, I can establish the relations for, you know, for both real and imaginary part of the eigenvalue lambda. For instance, for lambda r and for lambda I have, you know, these kind of expressions. And if I use this, you know, this equation, this is basically, you know, the imaginary part. So then you will see that, you know, I can get the expression for the real part of the eigenvalue, or you can say that the real eigenvalue, and for this parameter p. So both of these two guys, now they will depend on, you know, this, you can say that this eigenvalue, let's say, which is pure imaginary. And then you will see that these, you know, the trigonometric functions like sine and cot, they will appear in picture. And then because of, you know, the periodicity of these trigonometric function, many curves are traced out. As you know, this guy varies from, let's say, from -infinity to +infinity, and this will produce basically, you know, infinite number of curves. Okay, so for instance, you can see over here. So lambda is complex, and this is between lambda r and a. So for complex eigenvalue lambda, we have, you know, infinite number of solution curves. So you can see over here, I know, these guys and then these guys. And this eigenvalue is basically, you know, it's you know, it's real and it's natural. Okay. Now we can write down, you know, the general solution of our delay differential equation in this fashion, where sum is, you know, is taken over, you know, all the values of lambda n for a given parameter a. And then we see that, you know, for all values of a, which are, of course, I mean, we have, you know, all eigenvalues which have basically, you know, negative real parts, then this guy, your equilibrium solution, is basically, you know, stable, and it has, you know, this steady state. So this means that, you know, if a is from this particular interval, it's an open interval. Maybe we are not sure for this point at the moment. Okay, and now one can ask that, okay, what is that guy actually? And what is the value of this A sub C2. So it's nothing but it is the value, where you are, this guy is exactly equal to 0. Okay, but this is not true for your, let's say, the other value, which is pure imaginary. Okay, so if I go back to this equation, equation 8, which basically speaks about the real part of your complex eigenvalue, then you will see that if I choose this guy to be 0, okay, then I will get the following expression for lambda I. Okay, so your key is basically an integer. Okay. So if I go back to equation 9, then you will see that I'm able to express this parameter in terms of these eigenvalues, right? The minus and the plus, of course, the pure imaginary. Okay. So now from these two equations, where is equation? Yeah. So from this equation, which is basically an expression for this parameter A, and equation 15, which is over here. So you will see that the values of A, where each of infinite number of complex eigenvalues, they passes to this point. Okay. So since we know that the values of A are positive, so we really don't care about this, because since we already know that the real eigenvalues, they are positive. So if they are positive, so it's mean that of course our this equilibrium solution is basically unstable and mismatched. Okay. Now on the other hand, if we have the negative values of this parameter A, then the first crossing is at this particular point. Okay. Then if you go back to equation 4, you will see that this point is basically minus pi by 2. Okay. So on the other hand, you can say that if your this parameter is from this open interval, so then we will have this equilibrium solution as a stable equilibrium solution. Okay. Okay. So next, I will give you some let's say stuff which is about method solvers in order to solve delay differential equations. So if we have a delay differential equation with constant delays, or we can have delay differential equations with general delays. On the other hand, for instance, we can have delay differential equations with let's say that's neutral type of delay differential equations. So then you can use let's say these solvers like DDE 2-3, DDE SD, and DDE and SD in order to tackle the problems which are basically, let's say, of these particular methods. Okay. So let me choose one of the solvers, say for instance DDE 2-3 for delay differential equation with constant delays, and here is its syntax. Okay, so it demands let's say to write down the code for the given delay differential equation, and then of course you have to introduce delays, the lags, and you have to write down the code for the history function, and then of course you can set some interval where you want to integrate your delay differential equations. So for instance, for this argument, okay, so I mean the arguments are like for instance, if you take this function, so this function will basically evaluate the right hand side of your delay differential equations, and this function must have this form. So your t is your, of course, the current time, and then this guy is basically a column vector that basically will approximate your let's say solutions YFT. And this fellow Z is basically, going to approximate your delays actually, or the lags. Okay, and the lag is basically, it's a constant vector with positive delays. Okay, so you can have, let's say, a vector with many rows and one column, and you can put these positive numbers as for the lags actually. Then the history function. So for history function, for instance, if you just imagine, you have a constant history function, then you have to write down, let's say a column vector. Okay, and you can write down, some time interval. Okay, so for instance, maybe some initial time, and then the final time that you want to integrate your ordinary differential equation. So I would recommend you to read this description by yourself, okay, and try to understand it. Okay. Now, I choose this special case of, let's say, delay differential equation with constant delays. Okay, so I choose this as an example. Okay, so yeah. So now the point is, if I use this delay differential equation with constant delays, so I will use, of course, this, ODE solver, and my delay differential equation is basically with this, let's say, the constant history. So the history function could be even, the constant, okay? So now, if you just play with this, and maybe I can try, this example on live editor. Okay, so it's going to take some time. Okay, so I can basically, take output on the right hand side. Okay, now I choose this special case, delay differential equation with constant delays. So as an example, I have this, system of. Okay, so I pick one of them. Let's say this MATLAB solver DDE to 3, and other to attack, let's say, delay differential equations with constant delays. Okay. Here is the syntax for DDE to 3. Okay, so it demands basically to code the given delay differential equations. You can say that it will help you to evaluate, the right hand side of your delay differential equation, the system of delay differential equations. And then you have to build basically a vector with constants, which will contain some numbers, which will basically, tell you about the delays corresponding to your system of delay differential equations. Okay, so we have to write down a history function. This history function basically will tell us, about the behavior of the dynamical system in the past, actually. Okay, so for instance, it could be a constant vector like this, actually. Okay, and then you can establish a time interval. Let's say you can choose some, initial and final times where you want to basically, integrate your delay differential equation. Okay. So you can read these arguments by yourself, although I have given, a brief detail, and I would recommend you to read it by yourself. This, the description for this solver DDE 2-3. Okay. So now I choose one special case. So this is the delay differential equation with constant delays. Okay, and I try it with you know with live editor. Okay, and yeah, okay. So here I have to solve this, systems where I have three delay differential equations, and I had to make use of this DDE to 3 in order to solve it. Okay. So here the history function is basically for this particular time, and it's a constant basically. So you can see that it's, let's say, 1 for y1, y2, and y3. Okay. So now, I mean, I have to code, not only, you can say that this system of, delay differential equation, but I have to code the history function. And then, of course, I can use this MATLAB solver to solve this, a very simple example. Okay, so in order to code delays, so let's say in this particular example, we have two kinds of delays. So one is, let's say, 1, and the other one is 0.2, because it's clear from, from here. We have, yeah, one is 1 and the other guy is 0.2. Okay, so ODE solver basically accepts a vector argument for delays. Okay, so for instance, it's over here. So this is, you can say, corresponding to your first delay differential equation, and this delay is corresponding to your second delay differential equation. Okay, so as we have, nothing for the third delay differential equation. Okay. Next, you have to code your given delay differential equation, and you have to use this signature. Okay. So here T is, of course, your independent variable, the time, and this guy is basically, you can say that solution for your delay differential equation, and this guy will basically, approximate your delays for your delay differential equations. Okay. So, for instance, here I have two delays, which are, and let's say in these terms, y1 and y2. Delays are 1 and 0.2. Okay. So the first guy, let's say 1, is corresponding to y1, and the other guy 2 is corresponding to y2. And then you just give a look at the nature of your given delay differential equation. So for instance, here we have a system contains 3 delay differential equations. So you can write down, this very simple example. And then, of course, you have to code your history function. Okay, so in this case, my history function is a constant, which is basically 1 for all 3, delay differential equations, like for y1, for y2, and for y2, which is 1 actually. So it means that I can basically construct a vector with, let's say, 3 rows and 1 columns, and it contains all the 3 components, which are basically 1. Okay, and then I can just solve this equation by calling, of course, this ODE solver on this time interval. Okay, so if I just run it, then you will see that I will get 3 solutions for this system. So they are like let's say y1, y2, and y3 with these kind of behaviors. So we are not gonna say something about further on the behavior of the solutions of delay differential equations. Okay, so yeah, next I give you some extra reading material for delay differential equation. I would highly recommend you to visit this page, of course, the Scholarpedia page, which contains a lot of information about delay differential equation. one can visit the homepage of Professor Champagne, and also, this very nice document about, numerical methods for delay differential equations. Of course, we are not discussing numerical methods at this stage, but just for, a record. So you can even, give a look at the homepage of, Professor Zinaro and Alfredo Berlin, okay, these two Italian guys. And of course, there's a very nice document with the title is Differential Difference Equation, Delay Differential Equation by Bellman and Co. Okay, and I would like to recommend you to give a look at this topic as well. This is about stiff delay differential equations. Okay, so if you just visit this, I would like to see this page. Yeah, this page over here. This is stiff delay differential equations, and this is by my PhD advisor Guglielmi and collaboration with Ernst Harrier from University of Genoa back in Switzerland. Okay, so if you like, you can read further details. Anyway, and then yeah, so you can visit this Scholarpedia at this particular reference. And then finally, I give you maybe a couple of exercises. So already we have seen this exercise. So take this history function, and over this time interval, use method of steps in order to compute the solution for this delay differential equation. Okay. And even you can do one thing more. You can just vary, this history function, and you can study, the solution corresponding to this, delay differential equation by using method of steps. Okay. Goodbye.